All right, so let's take a look at this. You can kind of check your answers. Those of you who don't have it done, don't look. Just do it on your own and then check it later. It'll be on SharePoint. But you can go ahead and take a look at these. I'll scroll it down. A couple of things I want to comment on here. First, I want to make sure that you remember that weak acids and bases don't break up. Strong ones do. If it says it's aqueous or in solution, it breaks up. If it says it's a solid or a liquid, it does not break up. There are also the weird ones, like in question 1 up here, that you get hydrogen carbonate, we have to remember breaks up into water and carbon dioxide. So just kind of something to consider there. I'll scroll down so you can see the rest. Just hold up. So you can. And like I said, if you've got a bunch, you don't worry. I mean, I put this on SharePoint, so you don't have to copy them all down. I just wanted you to be able to quickly kind of see how well you did on various ones here as you go. Okay. All right, so check that. The other thing that we did yesterday was that second titration. How far did you guys get? What part did you get to yesterday?
D.
Finished D. D? That's all right. First I thought you said B. I was getting concerned. Okay, so did a lot of you get to E? Part E-ish? Okay. So what we're going to do next is we need to kind of run through that. So let me pull it up. You guys can refer to this part, like I said, on SharePoint. Ooh, that's going to be off to the side. All right, remember we did parts A and B in class yesterday. So what I want to do is to just kind of whip through C, D, and E, and then make sure you have a chance to try F and make a couple of comments on that. So if we take a look, here's C. We did A and B together. So here is part C. And with part C, this was very much like B, except we have added a little more base, but we're still not to the equivalence point. So as you can kind of see up here, what we're left with is still the hydroxide is in excess and is limiting. So we're left with acetic acid and the acetate ion. So both of those are there to impact the pH. And plug it into the mice table, just like before. So we have to account for our new volume, which is now 99.9 milliliters. Lose some, gain some, plug it into the expression, solve for X, take the pH, which you get is 7.44. You guys get that number? Okay, part D, we're now at the equivalence point. The equivalence point, of course, being the point where we have exact number of moles of acid and base. So we are run out of everything, and the only thing that's left in the solution is the acetate ion. So here's where I would change equations now, because when I think about trying to find the pH of a saltwater solution, I think the salt reacts with water. And so that's what I've done here. As I look at this equation, I'm reacting the salt with the water to produce the hydroxide ion concentration. Take that number of moles, divide it by my new volume, which is 100 milliliters in this case. Lose some, gain some, but I'm plugging it in. Now it's a KB. It's not the KA anymore. So it's writing the KB equation. So since I gave you the KA, I've got to divide it by KW divided by the KA to find the KB. And then I can plug it in. X now is the hydroxide ion concentration. I can take the POH and then find the pH, 9.23. Okay. What happens in part E? What shifts? What's different now? Danny?
The OH minus is in excess.
Right, the OH minus is in excess. So as we look at part E now, ignore what I haven't read for just a moment. Let's just look at this table up here. In part E, now acetic acid is limiting, and we're left with some leftover hydroxide as well as some acetic acid in solution. For those of you who got to this part, you should have set a table up like this, right? Those of you who got there? Did you get X being like 2.8 times 10 minus 7?
Yeah.
Okay. So if we just look at what's in red right here, and you think, okay, I have acetate ion and I have hydroxide ion. The best equation that's going to contain both of them is this one here, that the acetate in the water producing acetic acid and hydroxide. And you can look and you can plug in your molarities and go ahead and go through and solve for X. And we get X being 2.8 times 10 to the minus 7, which when you add 2.8 times 10 to the minus 7 to this 0.0010, what is that quantity? 0.0010. That X is so negligible, it doesn't matter, it won't impact that because it's too small. And what that really means, and I wanted you to do it this way, although I'm not showing that to you. I wanted you to do it this way because what I want you to see is that when you have hydroxide, which very directly impacts the pH, and a weak base, which will grab a hydrogen from water to form a small amount of hydroxide, the weak base isn't going to have much of an effect. This is how much of an effect that weak base has in contributing to the OH minus concentration. It's adding this 2.8 times 10 to the minus 7, hardly anything. So as we work through titration problems, that's why I have this written here. When OH minus is in solution, the weak base is contributing a negligible amount of OH minus. So we can ignore it. So the only thing I need to consider is that the OH minus is impacting the pH. I can just ignore the acetate ion, which makes it really, really simple. Because now I just need to take the molarity of the OH minus, moles divided by this new volume, take the POH and subtract from 14. Those of you who did it with this equilibrium, did you get 11?
Yes.
Yeah, you did. Okay? So it just to kind of emphasize to you that difference that the acetate ion makes is negligible. So what I'd like you to do right now is to do letter F. If you've already done it, fine, just hold out for a second. Those of you who haven't done letter F, I want you to just do it very quickly. And based on what I've just talked to you about, that shouldn't be a difficult thing for you to do. So go ahead and do letter F. Oh, all right, let's get back to this thing. Oops, wrong button. Okay, so what did you guys get? 13 point something, right? 14.52, yeah, whatever, something like that, right? So if we take a look at this, and you can kind of peek here, same basic idea. We have hydroxide in excess. So, I mean, the concentration of hydroxide is even more in this case, so it's even more appropriate to exclude the acetate ion. But if you don't want to, you can go through all the equilibrium stuff. I mean, it's totally cool. You get the same answer as me. I'll just save a bunch of steps. And so I can find the concentration of hydroxide and POH it and subtract it from 14, and we're good to go. Right?
Yeah.
All right. So now what we need to do is to compare this one versus the old one. So remember on the first problem, I had you do a quick sketch of pH versus milliliters of base added. Right? Come on, people. Like the other day? Hopefully yours looked kind of like this-ish. Does it have this shape? Yeah. Okay. So that's what we need to look at right now. Let me pull up. There we go. Oh, but let's make it smaller so we can see it better. So here's a basic graph of that. Oops. Let's remake that line I just erased. And as we look at this graph, there's a couple of things I want you to notice. First of all, this is that point around 49.9 milliliters of base added, pH around 3. 50 milliliters of base added, pH around 7. 50.10 milliliters of base added, pH around 11. I want you to notice here this inflection point, because when you look at a titration curve like this, you should notice that there are two curves. There's this one curve that has kind of this shape to it, and then there's this other curve that has this shape to it, and the point where that one curve starts turning into the other curve is the inflection point. The inflection point is the equivalence point of a titration. So for any kind of a titration graph like this, you can identify the equivalence point by looking for the inflection point on that graph. And for us, that inflection point is turning here at pH of 7. For this is the strong acid, strong base one. So as we look at this, I've got 3 different indicators up here and the approximate pH at which they change color. We have methyl red at a pH of 5, bromothymol blue at a pH of 7, and phenolphthalein at a pH of 9. And so here's my question to you. If the equivalence point is at 7, why in Chem 1 was it okay to use phenolphthalein? Why was it okay to use if our equivalence point is at a pH of 7? Chris, what do you think?
Because we were titrating acetic acid.
Well, one of the titrations you did was acetic acid.
Right, okay, so...
But you also did this one. In Chem 1, you always did HCl. You probably did HCl first and then acetic acid. So why is it okay here?
Well, in this case, like the line, like the slope is so huge that like where the concentration at which the pH is 7 and the concentration at which pH is 9 are like negligibly close together.
Yeah, that's exactly. I mean, this line gets pretty vertical right in here, right? And so if you think about it, if we really consider for a moment, here's our pH of 3. Up here is our pH of 11. What's the volume of sodium hydroxide that was added to get from pH of 3 to 11? 0.2 milliliters, 0.2 of a milliliter, from 49.9 milliliters to 50.1 milliliters. We are interested in this pH of 7. So to go from a pH of 7 to a pH of 11, how many milliliters were added? A tenth of a milliliter, right? So if you were to guess, how many milliliters would it take to get from pH of 7 to a pH of about 9? Half of a tenth, right? 0.05 milliliters? How big is a drop? Probably bigger than 0.05 of a milliliter. Okay? Or at least around 0.05 of a milliliter. So my question to you is, if in fact you're close to the equivalence point but not there, and you add 1 drop, because we want the equivalence point and the end point to be as close as possible, if you add 1 drop, is it okay to use phenolphthalein? Are you within 1 drop of the equivalence point? Absolutely. And why is phenolphthalein better than, say, bromothymol blue, who changes at 7? Why? Change in color, yeah, it's more obvious. Okay, it's not like blue, green, 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 blue. What shade of green are we looking at? So it's a lot easier to look at. All right, now let's going to compare. I'm going to show you the same graph, but with the second titration that we did added onto it. So what's in blue here is that first one. We just talked about it. That's from problem 1. What's in red is from the second problem. And I want you to notice a couple of things. One is sort of this little bit of change in the shape of the curve at the very beginning right here. That's fairly typically, we didn't do all those points, so you wouldn't see that if you were to graph this. But if we were to either experimentally or by numbers graph this, what we would find is it's got a little bit of a different curve to it there at the very beginning. Of course, we see that the pH is starting out much higher. The two mimic each other past the equivalence point. And that goes back to the idea that the acetate ion that's produced really doesn't affect the pH that much. It's all about that extra hydroxide, and they both have the same amount of extra hydroxide. An inflection point between this first curve and the second curve, that's occurring up here. We know it's at 9.23. But let's talk about indicators. Is it okay to use phenolphthalein in this particular titration? Would phenolphthalein have a color change that's close to the equivalence point? Yeah! And guess what? You guys titrated vinegar in Chem 1. Okay, that's acetic acid. So yeah, that's totally okay. How about methyl red? Methyl red is going to change here. It's going to change color over here. Are you close to the equivalence point? No, you're not. So that's not going to be a good choice for this particular titration. What about bromothymol blue?
Yes.
What's the volume difference between here and here?
Not much.
Not much. Could you use bromothymol blue?
Yeah.
You could. I mean, we have the issues of it might not be easy to tell, but would it change around like within a drop of the equivalence point? Yeah, it probably would. So we have to be careful as we look at our indicators to make sure we make the right choice. In Chem 1, phenolphthalein a great choice. It's 1 drop away from your equivalence point. That's what we want. And it doesn't matter if it's a weak acid or strong acid. In fact, you did both. So it's a great choice. Tomorrow, we're going to be doing a lab, and you're going to be doing a titration with phenolphthalein. But you're all experts at titrating, so this is not going to be a problem for you. So what I want to do is to mention a couple of things about this lab for tomorrow. We're going to be doing, you're going to actually be generating in part 3 a titration curve with the lab quests back there. But we're going to be doing experiment 15. However, there are 3 parts in the lab, and we're only going to do 2 parts. So we're only going to be doing part 1 and part 3. So that's why I kind of have the specific instructions for your homework about only do pre-lab questions 2 and 4, because those are the ones that deal with the 2 parts we're doing. And when you write up your lab notebook and you're writing up the procedure stuff, just do parts 1 and 3, because we're not going to do part 2. Bye, Sven. So I want to just kind of make a comment about the lab very briefly, and then we'll be done. So tomorrow's lab, there's going to be 2 parts. Like I said, parts 1 and 3. Part 1, you are going to be standardizing the sodium hydroxide. You don't know what it means to standardize? What do I mean by standardizing the sodium hydroxide? Make it normal. Well, we'll have it back there. It's a big container of sodium hydroxide. We're not going to make it happy. Standardizing means we need to figure out its exact concentration. And sodium hydroxide is a little strange because you might say, well, why don't I just calculate how many grams and turn it into moles and divide it by the volume of the solution and I have my molarity, which is great, except that sodium hydroxide absorbs water. The solid form of sodium hydroxide absorbs water. And so it's difficult to know what the dry sodium hydroxide's mass actually is. So it's fairly typical to standardize it. And we're going to standardize the sodium hydroxide really by titrating it with a weak acid. That weak acid is KHP, potassium hydrogen phthalate. It's a solid weak acid, which you'll be making into a solution and titrating it in order to determine the concentration of the sodium hydroxide. That's what you're going to do tomorrow. So you're going to do a couple titrations tomorrow. Then on Monday, I'm going to give you an unknown acid. And your job is going to be to find the Ka of that unknown acid. So in order to do that, I want you to think about some of the things that we've already talked about in our past. Let's say it's this unknown acid, HX. And we can write our expression, all this stuff like we've already done many times. And I'm going to rearrange this in a very similar way as when we were talking about indicators. So if I make it Ka over H plus is equal to X minus over Hx. Now, you're going to be reacting this unknown acid with the sodium hydroxide you standardized. I'll just do OH minus. So the neutralization reaction is going to be this. Well, if we look at the point when these two are equal, it should look familiar, then what will also be equal? Yeah, so if X minus is equal to Hx, then Ka is equal to H plus, then the pKa is equal to the pH, and we'll be having some pH meters, so we can record pHs. And you'll be developing a graph. Oh, that's a terrible graph. Wow, it's a weak acid, so we'll make it kind of look weak acidy. pH versus base added. And so the biggest question starts to become, when is Hx and X minus equal? When is Hx and X minus equal? At what point in the titration are those two equal to each other? This and this. And yeah, I'm asking you now. Talk to your partner for the next like 15 seconds. Figure out when along the course of the titration will Hx and X minus be equal. You got about 15 seconds. Go. I don't know, we're over 15 seconds, but you sound good over here. Not here. I don't know what's going on here. All right, do we have an answer? When in the course of the titration will they be equal?
The equivalence point.
Why?
Because are they conjugate acid-base pairs?
Well, what happens at the equivalence point?
That's when they neutralize each other.
So will you have any Hx left at all at the equivalence point?
In theory, no.
No. At the equivalence point, all of the Hx and all of the OH minus will be gone. So we will have X minus, but we won't have any Hx. So when, we still have to have Hx left, when will we have an equal amount of Hx and X minus? It must be before the equivalence point. Equal amounts. Because here's my equivalence point.
Halfway along the curve.
That's exactly right. Halfway. Halfway along the curve. So if I know it takes, I don't know, 10 milliliters of base, halfway there, 5 milliliters, would be this point, halfway to the equivalence point, we would have a case where the concentration of Hx and X minus will be equal. In which case, halfway to the equivalence point, the Ka is equal to the hydrogen ion, and the pKa is equal to the pH. We're going to be using that on Monday. That's where we're headed. Okay? How what?
Is that just something that's been observed, or is there...
Well, because if this is equal number of moles of acid and base, then if we added, think back to our titration, if this is adding 0.05 moles of, if we have 0.05 moles of acid and 0.05 moles of base, if halfway there we add 0.025 moles of base and you have 0.05 moles of acid, in fact, let me show you. Back to, I'll show you this one because I have this example. Think of this. This was the one I just showed you. Actually, this was B, which we had done yesterday. You weren't in class for. But at B, halfway, this was halfway to the equivalence point. we used up half. We were left with equal moles of acid and equal moles of the base, because it's the point where you're only adding half of the moles that are required to neutralize it. Okay? All right, so you guys got pre-lab tomorrow, notebook and the questions. And we'll see you guys tomorrow.